Crude oil contains a mixture of different hydrocarbons, which we separate into fractions using fractional distillation. However, the proportions we obtain don't always match the quantities we actually need. We often have too many of the long-chain hydrocarbons and not enough of the short-chain hydrocarbons, which are in much greater demand. So how can we convert these larger, less useful molecules into smaller, more valuable ones? Well, the answer lies in a process called cracking, and in this video, we're going to be looking at what cracking is, why it's so important to the oil industry, and the two methods used to carry it out on an industrial scale. But first, what exactly is cracking? Cracking is the process of breaking large hydrocarbon molecules into smaller hydrocarbon molecules. And you might also see this described as breaking long-chain hydrocarbons into shorter-chain hydrocarbons. Both descriptions mean exactly the same thing, and ultimately it wouldn't matter which of those you chose to use in an exam. But before we go any further, it's worth us just taking a moment to think about what this actually involves. These large hydrocarbon molecules aren't simply snapping or breaking apart on their own. Each hydrocarbon molecule is made up of incredibly strong carbon-carbon and carbon-hydrogen covalent bonds. So if we want to split large hydrocarbon molecules into smaller ones, we're going to need to supply a lot of energy to do so, which ultimately is going to cost quite a bit of money. So this then begs the question, why do we even bother? Well, if we think back to the problem we discussed at the start of the video, we get our answer. Long-chain hydrocarbons are produced in much greater quantities than what we actually need. Whereas short-chain hydrocarbons, those predominantly used as fuels, are in a much higher demand, and we simply don't get enough of them through fractional distillation. By cracking long-chain hydrocarbons into shorter ones, oil companies can effectively convert less valuable products into more useful, more desirable, and ultimately more valuable ones. The sale of these more valuable products then makes more money than what was spent on the process itself. So cracking is much more than just an interesting chemical process. It's an incredibly important economic process as well. Without cracking, the oil industry simply wouldn't be able to meet the demand for many of the fuels and chemicals that we rely on every single day. So when we crack these large hydrocarbon molecules, which are predominantly alkanes, are we just forming lots of shorter, more valuable alkanes? Well, no. And to understand why, we need to think about what happens to the atoms during cracking. When a large hydrocarbon molecule is cracked, it doesn't simply turn into lots of smaller versions of the same type of molecule. Instead, the original molecule is broken apart and rearranged to form a variety of smaller hydrocarbons. The exact composition of the products formed depends upon the conditions used and the type of cracking that is taking place, which we'll look at later. But the products of cracking include smaller alkanes, alkenes, cycloalkanes, and even aromatic hydrocarbons. Now don't panic if you haven't come across aromatic hydrocarbons yet, the detailed chemistry behind them is actually part of Year 13 content. But for now, all you need to know is that aromatic hydrocarbons are simply another type of hydrocarbon structure that can be produced during cracking. But despite this diverse range of products that can be formed, there is one key principle that always applies, and that is that during any chemical reaction, atoms are always conserved, which is the reason we can't only make lots of alkanes. To show this in action, let's imagine we're cracking a molecule of decane. Now I know 10 carbon atoms isn't a particularly long chain, but it helps to illustrate a point nonetheless. Now when carrying out cracking, we don't know exactly what products we're going to form, and that's one of the exciting things about cracking. We can change the conditions and method used to influence the types of products we're likely to get, but we can never control exactly how and where the hydrocarbon chain is going to break. So we cannot predict the exact composition of the products that will form. However, what we do know is that we're starting with a molecule that contains 10 carbon atoms and 22 hydrogen atoms. Therefore, we know that our products must also contain 10 carbon atoms and 22 hydrogen atoms in total. Remember that during a chemical reaction, atoms can neither be created nor destroyed. They can only be rearranged to form new or different substances. And it's this principle, the conservation of mass, that explains why cracking cannot simply produce lots of smaller alkanes. For every carbon atom in an alkane, there are enough hydrogen atoms attached to make the molecule saturated. But when we split one large alkane into multiple smaller molecules, we haven't added any extra hydrogen atoms. This means that there simply aren't enough hydrogen atoms available for every product to become an alkane. Therefore, at least one of the products must be something other than a simple saturated hydrocarbon chain. This means we have to form products such as alkenes, cycloalkanes, or aromatic hydrocarbons alongside any alkanes we may make. For example, we could crack our decane molecule and form octane, using 8 of the carbon atoms and 18 of the hydrogen atoms, leaving 2 carbon atoms and 4 hydrogen atoms to form any other products, and so ethene would also have to be formed. But this isn't the only way decane could end up being cracked. The hydrocarbon chain might break apart differently, forming heptane as our first product. This then leaves 3 carbon atoms and 6 hydrogen atoms, which could form butene, or even cyclobutane. Remember, alkenes and cycloalkanes are functional group isomers of one another and so have the same molecular formulae. Rather than just forming 2 smaller hydrocarbon molecules, we could also end up with multiple products being formed. During the cracking of decane, the hydrocarbon chain could break in such a way that pentane is formed as one of our products. Since that would use 5 of our 10 carbon atoms and 12 of our 22 hydrogen atoms, that would leave 5 carbon atoms and 10 hydrogen atoms to form any other products. Now, it's entirely possible that pentene or cyclopentane could be formed as a single additional product. But propene or cyclopropane and ethene could also be formed using those remaining atoms. It's also entirely possible for multiples of the same product to be formed. Decane could break apart in such a way that we end up with butane and then 2 molecules of propene or cyclopropane. But the important thing to remember is that although when cracking large hydrocarbons into smaller ones, we can have lots of different products being formed, the atoms involved in the reaction are always conserved. The total number of atoms of each element before the reaction has to equal the total number of atoms of each element after the reaction. So now that we know what cracking is and the types of products we can form, let's have a look at what actually goes on during cracking to break those large hydrocarbon molecules apart. Well, we've already said that cracking requires a lot of energy, and this is because we're breaking strong carbon-carbon and strong carbon-hydrogen covalent bonds. And the presence of these strong bonds in alkane molecules is one of the reasons why they're relatively unreactive molecules. But what does all of that mean for cracking? Well, the process of cracking is going to require high temperatures, and those high temperatures are needed in order to provide sufficient energy to break those incredibly strong bonds. And this is actually a really important concept, and one that often comes up in exam questions. Regardless of the method used for cracking, high temperatures are needed to break the strong carbon-carbon and the strong carbon-hydrogen covalent bonds. And as I've just alluded to, there are actually 2 different methods of cracking that you need to be aware of for A-level chemistry: thermal cracking and catalytic cracking. Both methods ultimately achieve the same goal. They both break large hydrocarbon molecules into smaller ones, but they do so under different conditions, and as a consequence, they produce slightly different mixtures of products. Let's take a look at each in turn, starting with thermal cracking. As the name suggests, this method relies primarily on heat. Thermal cracking is carried out at incredibly high temperatures, typically around 700 to 1200 degrees Celsius. Thermal cracking is also done under high pressure, usually somewhere in the region of 70 atmospheres. Now, those are incredibly harsh conditions, but remember, we're trying to break the strong carbon-carbon and strong carbon-hydrogen bonds, so a large amount of energy is needed. Now, I've just given you the values for the temperature and pressure at which thermal cracking is carried out under, but don't worry about trying to learn these values for your exams. You don't need to. All you need to know is that thermal cracking requires a high temperature and a high pressure. The other thing you need to know is what types of products are favoured by thermal cracking. Thermal cracking tends to produce a lot of alkenes, and this is one of the reasons thermal cracking is so useful. Alkenes are incredibly important starting materials in the chemical industry. They're used to manufacture many everyday products, particularly plastics like polyethylene, through addition polymerization. Now, don't worry if you're not familiar with that process yet, we'll cover polymerization later in the course. For now, it's enough to appreciate that alkenes are valuable because they can be used to make lots of other useful chemicals. So thermal cracking requires high temperatures and high pressures and tends to produce a greater proportion of alkenes that can be used as chemical feedstock and to manufacture plastics. But what about our second industrial process, catalytic cracking? Well, again, as the name suggests, this method uses a catalyst, specifically a zeolite catalyst. Zeolite is technically a hydrated aluminosilicate, but you really don't need to worry about that, and I personally just stick with calling it zeolite. The zeolite catalyst provides an alternate pathway that lowers the activation energy, allowing cracking to take place more readily. As a result, catalytic cracking can be carried out at a slight pressure, but still requires a high temperature, generally of around 500 degrees Celsius. But again, you don't need to know the specifics. The trap students fall into, however, is linking the lower temperature requirements of catalytic cracking compared to thermal cracking with the idea that it therefore requires a low temperature. It doesn't. 500 degrees Celsius is absolutely still an incredibly high temperature, and despite the use of the zeolite catalyst, a high temperature is needed because of the strong carbon-carbon and carbon-hydrogen covalent bonds. As with thermal cracking, you also need to know what types of products you're more likely to form when using catalytic cracking. Catalytic cracking produces a higher proportion of branched-chain alkanes, which are commonly used as motor fuels, and aromatic hydrocarbons. So although both thermal and catalytic cracking break large hydrocarbons into smaller ones, they're often chosen for different purposes depending upon which products are most valuable. Comparing the two, both processes break long-chain hydrocarbons into smaller, more valuable hydrocarbon molecules. Thermal cracking uses high temperatures and high pressures, producing a larger proportion of alkenes, whereas catalytic cracking uses a zeolite catalyst at a high temperature and slight pressure, producing a greater proportion of branched-chain alkanes and aromatic hydrocarbons. At the beginning of this video, we asked why the oil industry carries out cracking. We've now seen that cracking allows larger, less valuable hydrocarbons to be converted into smaller, more useful ones. We've seen why cracking produces a variety of different products, why high temperatures are always required, and the differences between thermal and catalytic cracking. In the next lesson, we'll look at one of the biggest reasons these smaller hydrocarbons are so valuable, by exploring how alkanes burn as fuels and some of the environmental issues that combustion creates. If you'd like to continue with this topic, the full playlist is on your screen now, and if you found this helpful, please consider subscribing for ongoing support with A-Level Chemistry.